Hi students, now we'll talk about section 13.2 simple harmonic motion. Let us look now at the oscillations. When we use oscillation function, which is sine or cosine, we will see that now. This motion means that the body is moving, go and forward and backward many times during a period time t. You will see videos explaining that, but this sinusoidal motion will be represented by a function. This function is sine or cosine, we will see that. And the shape of this function is, as we see here, sinusoidal. This wave has some properties. We will not deal with all of these properties, but we will need to look at them. When we look at the point and another point on the function are the same points repeated always, this means we have a complete wave. A complete wave. If we start from here to here, this is a complete wave. The length between two corresponding or symmetry wave points, then this length is called lambda. Lambda is the wave length. This distance from zero to the top of the wave named A, which is amplitude, which is the maximum distance that the body move in its oscillation. So look here, if we at t equals 0, we have this is x t graph, which is position time graph. At t equals 0, we have amplitude maximum displacement a0 or a0. After a while we have a1 from 0 to the maximum distance. Also for a2. Also we have minus a. We note that a0 is equal to a1, which is equal to also to a2 and equal to all a's. This simple harmonic oscillation, this motion is undamped. It's continuous and uniform. But if we look to this wave, we have a0 and then a1 and then a2. We see that the amplitude of the wave is reduced by the time. The wavelength is the same. There is no change in the wavelength. We can compress the wave and or expand it, then the wavelength will be exchanged during that. But the wavelength is also the same. Also here, if we choose 2 points, corresponding points, P and P, have the same position and the same slope at that point. The slope at this point is negative, and the slope is here is also negative. We can see this point, which we can name it D. It is the same position as P, which is negative 3, for example. But it is not the same point, because in this point the slope is negative, but here the slope is positive. Here means that the body is going away, but at this point meaning the body is coming back to the 0 position. Okay, let us go back to this damping oscillation. We can see after a long time the wave amplitude will reach 0. This is damped oscillation. Okay, we will not deal with this and this. You can see them experimentally in the lab, but in general we will deal with the sinusoidal constant oscillations. Okay, we also need to remember that the frequency is equal to 1 over the time period, T capital. Also, omega, which is the angular velocity, is equal to 2 pi, which is the total rotation, over the period. Using these two equations, we can find that omega, which is angular velocity, is equal to 2 pi if 2 pi multiplied by the frequency. These are three relations. We know two of them. This is the third one if we combine the first two of them together. Okay, now let us look at these functions. I think you see before cosine function and sine function. I use here the graph between time or between x and the function cosine of x. Cosine of x in this case is multiplied by 1. We know that sine and cosine has maximum value and minimum value. The maximum value is 1 at x equals 0, for example, and which is equal to minus 1 at x equal pi, which is 3.14. This is cosine theta multiplied by 1. This one is the maximum value of cosine is 1 multiplied by 1. Then the answer is 1. The amplitude and the maximum value of cosine is 1 and minus 1 and plus 1 and minus 1. In general, the amplitude is 1. Okay, and the wavelength, it is between two symmetric points between 0 and 2 pi. This is 6.28, which is 2 pi. This is pi. This is pi over 2. Pi over 2 means 90 degrees. 90 degrees. Cosine 90 is 0, and this is 0. Look at this function, which is 1 cosine. It is the same. X, the same, plus 2 pi. 2 pi means that I move my function 2 pi to the right. In this case, that means I bring this point to the 0 position. What if I move all the function to the left by 2 pi? It will still the same. So the point of on the function, it is equal to its magnitude at the same function after 2 pi. Okay, but if we move it different than 2 pi, it will be different. There is a phase. Now, if we look at the sine function, sine function multiplied by 1, that means the maximum value of sine is 1 multiplied by 1. It will be the maximum value is 1. Okay, sine 0, it will be 0. Sine pi, which is 180, it is equal to 0. Sine 2 pi is 0. Sine pi over 2, which is 90, it is 1. Multiply by 1, it's still 1. In cosine function, cosine 0 is 1. Cosine pi minus 1, and so on. Also, if we add to the magnitude of x, to this argument, if we add 2 pi, that means we'll move the function to the left or to the right. If we put plus minus by 2 pi, that means if I bring this point to 0, it will still the same because the function is periodic and it has a symmetry nature. Okay, this if I take 1 multiplied by sine x or 1 multiplied by cosine x, this is the ordinary function, sine and cosine. But what if I take 3 sine? The maximum value of sine is 1. When I multiply it by 3, it will be 3. Okay, sine is 0. Is 0. Multiply by 3 is 0. Sine pi over 2, which is 90. Sine pi over 2, which is equal to sine in 90 is equal to 1. If I multiply it by 3, it will be 3. But look here, if the amplitude A, what I talked about it here, A here is 1. It is the same as the constant that multiply by that function. The amplitude here is a 3, which is the same as the amplitude of that function. But x, it's the same. So sine pi is 0, sine 2 pi is 0, sine pi over 2 is 1, sine 3 pi over 2 is minus 1, multiplied by 3, it is minus 3. Okay, now look, sine multiplied by 2, that means the amplitude will be 2. It is the same constant magnitude, okay? If I multiply it by minus, then the sign will be in negative direction. But I change x to 2x. Look here, the total wave is from 0 to 2 pi. This is 2 pi. Then from 2 pi to 4 pi. This is a total wave. Complete wave length, okay? But if I take it 2x, the complete wave, the total wave will be from 0 to pi. This is the total wave. From 0 to pi. But when the argument is just x, I have the wave from 0 to 2 pi. Look, when I multiply the argument x by 2, the wavelength is shorter by half. Also, if I multiply the argument x, this is the same function, but with multiplied by half. If I multiply by half, the wave function, now look at it. The total wave from 0 to 4 pi. Not to 2 pi. The original one is just to 2 pi. The wavelength is to 2 pi. This is 2 pi. If I divide it by 2 or multiply by half, then the wavelength will expand by 2. If I multiply by 2, then the wavelength will compress by 2 or by half. If I multiply by 3, then it will compress by 3. If I multiply by 5, if I divide it over 5, I will show you later, 1 over 5x, then the wavelength will be expanded by 5. So I need you to know that the constant that the function is multiplied by here and the argument which is multiplied by x or t inside the sine or cosine function, it affects the shape of my function. Maybe it increase or decrease the magnitude, the amplitude, or it will change the wavelength. If it is changing the wavelength, then the time period also will change. We will see that later. Okay, now for our system, if we have, for example, a spring system, if we compress the spring to amplitude A, for example, and release it, then it go to its relaxation distance, which is 0 here. This is relaxation. Then it will continue expanding to reach minus A, and then it will be go through oscillation, not damped oscillation like this one. This is in real life happened, and in the lab you will see that, but we are talking on ideal case. We don't have any relaxation or damping or any friction to make this wave going smaller and smaller in amplitude. So the amplitude is constant, A. If we look to this motion, if we start not from zero, if you look here, the sine function at 0 is equal to 0, but the cosine function at 0 is equal to a, not to 0. So this function is the same as this one. It is not starting from 0, it is starting from a. Okay? So this is the position function. We need to remember before that the time period is equal 1 over frequency, which is equal to 1 over 2 pi omega, because the frequency is equal to 2 pi omega. So the position function x of t is equal to a multiplied by cosine omega t. A is the amplitude, omega is that constant which is exist in our equations here. Okay, we can add 2 pi to our equation inside the cosine, but it's okay now. And omega, we know that omega is equal to 2 pi over t capital, which is the period, multiplied by t, which is the dependent value. This is the position function. Because this function, this particle or this object or this block is moving, then this object has velocity. This is a position function. We know from before, and you see that in the lab, that the slope of the function is equal to the velocity. In the first or the second lab, I think you see that. If I take the slope at the point, which is the instantaneous velocity, this slope is positive, as you see. That means that the velocity is positive. If we take it, this is the velocity function. At this point, the slope is 0. The tangential line is horizontal. Look at the velocity at this point. It is 0. What else? If we have a point, this point, the slope is negative. Look at this corresponding velocity. The velocity here is negative. This is negative value and this is positive value. At x equal to 0, it is the maximum amplitude. It is the same as this point here. And the slope at this point is 0. Look at this velocity, it is 0. Okay? Continue. If this body is going under a force, which is Hooke's force, and its weight force, then there is acceleration. We have position, we have velocity, we have acceleration. We know that the acceleration is the slope of the velocity graph also, as you learned before. If we take the velocity at this point, which is maximum point in velocity, the slope is 0. Look at the corresponding acceleration here. It is 0 acceleration. Look here, the velocity here is 0, but the slope for the velocity function is positive. Look at the acceleration here. The acceleration is positive. At t equal to 0, the velocity is 0, but the slope is negative. Look at the slope here. The acceleration is negative. That all of that is depend on the position of the body. When the body is at maximum or minimum points in its motion, then the velocity is 0. Look, this is the velocity 0, and the acceleration is maximum point, because the force here is maximum from that spring. When the object at its relaxation point, okay, which is at x equals 0. It has maximum or minimum velocity. Look at this point, it is at x equals 0. It's maximum velocity or it's at maximum velocity. Positive or negative, that depend on the direction of motion. At maximum velocity, we have minimum or 0 acceleration. Okay? So we have three functions. First of one is for position, which is cosine multiplied by the amplitude, and there is something inside. We will see that 2 pi over t multiplied by t. We can also add 2 pi to our function because it is periodic. The velocity function of t is equal to minus a omega sine omega t, plus we can put that plus 2 pi. It's okay. So, and the acceleration is minus a omega squared cosine omega t, and omega is 2 pi over t. It's the same. We will see that. We can add also 2 pi. So the position function is cosine, the velocity is sine, the acceleration is cosine. You will see that in the exam. You will be given these formulas to solve any example or question you need to solve. We will see that in the next section. Thank you.